The next periodic trend we are going to discuss is ionization energy. And ionization energy is the energy required to remove the most loosely held electron from an atom in the gaseous state. So if we look at a particular ionization energy, and the number of ionizations we can have is actually equal to the number of electrons a particular species has. So if we look at magnesium in its gaseous state, it can become magnesium plus 1 electron. It's going to require an amount of energy to do that. And the first ionization energy for magnesium is going to be equal to 738 kilojoules per mole. If we continue to remove an electron from that magnesium, we can get magnesium 2 plus another electron. And the second ionization energy is going to be equal to 1451 kilojoules per mole. And one thing I want to point out here when discussing ionization energy, the first ionization energy is the energy required to remove one electron from, in this case, magnesium. The second ionization energy is the energy required to remove one electron from magnesium plus. It is not the amount of energy to remove 2 electrons. Okay? That would be the sum of each of these ionization energies. So make sure you keep that in mind when we're looking at these. Another thing to say is that each succeeding ionization is larger than the previous one. So In is going to be greater than In minus 1. And you can see here that when we remove one electron, it takes 738 kilojoules per mole. And to remove that second electron, it jumps up. It almost nearly doubles. So what we can say, and we can generalize this trend, is that the further the electron from the nucleus, the easier it is to remove it. And the general trend in ionization energy that we're going to observe is ionization energy decreases as we move down in the periodic table, and it's going to increase as we move from left to right. So what we can say here, and one of the things that I have to indicate is I need to put a star here next to the increase, because this isn't going to be a linear trend. There is a jagged trend in this ionization energy. So to investigate this trend, let's look at the elements in the second period of the periodic table. So if we look at our ionization energies on the y-axis, and we'll look at the group number on the x-axis, and we can kind of start, we'll start with lithium. So lithium has a fairly low ionization energy. When we go from lithium to beryllium, as the trend suggests, the ionization energy is going to increase. But what we see is when we go to boron, we see a slight drop in ionization energy. Then it will increase again as we go to carbon, then up to up to nitrogen. We're going to see another drop when we go down to oxygen. Then it's going to increase when we go to fluorine, and then neon kind of goes off the charts. So the question is, why do we see this type of trend in ionization energy? And it can be explained if we look at the electron configuration. So if we look at lithium, our electron configuration is going to, or the number of valence electrons is going to be 2s1. For beryllium, we have 2s2. Boron is going to be 2s2, 2p1. Carbon, 2s2, 2p2. Nitrogen, 2s2, 2p3. Oxygen, 2s2, 2p4. Fluorine is 2s2, 2p5. And neon, 2s2, 2p6. And when we looked at electron configurations, there were some anomalous electron configurations, and they had to do with kind of how the energy of those electrons are going to result. So in this case, we can kind of see a little bit of stability going from beryllium to boron. There's a discontinuity in the linearity when we go from nitrogen to oxygen. And then everything else kind of goes linear. So the reason these gaps are here is because we find stability from a completely filled orbital, or in the case of nitrogen, a half-filled orbital. So it's a little bit more stable, and when we remove one of the electrons from oxygen, if this electron is removed, we now attain an electron configuration that gives a half-filled orbital. The same thing that happens when we look at boron. If we remove this electron, it now has a filled s orbital. So this is why we see a deviation from a linear trend for ionization energy. We can kind of take this ionization energy topic and we can look at and actually obtain values for each of these. So if we compared sodium and magnesium and looked at the ionization energies, the first ionization energy for sodium is going to be 496 kilojoules per mole, and I'll list all the units in this table in kilojoules per mole. And the second ionization for sodium is 4,592 kilojoules per mole, which is a drastic jump. If we look at magnesium, the first ionization energy is 738 kilojoules per mole. The second ionization energy is 1451 kilojoules per mole. And the third ionization energy is 7,733 kilojoules per mole. So here, for sodium, we see a large jump from the first to the second ionization energy, whereas magnesium, we see a large jump from the second to the third ionization energy. Okay, so this can be we can look back in the periodic table on the electron configuration. When we take one electron away from sodium, it has the noble gas core of neon. So it's going to be very, very stable. That second electron being taken away is going to require a lot of energy. Whereas magnesium, we take one electron away, it still has one valence electron left. So when we take away that second electron, it's going to reach its noble gas core. So to try to remove that third electron, it's going to take a heck of a lot of energy to do that. So we can kind of look at this then by saying, let's say we have an unknown element that we're going to refer to as X. The question is, what group is element X going to be a part of? So let's look at its ionization energies. We're given values for the first 4 ionization energies. So the first ionization energy is 578 kilojoules per mole. The second ionization energy is 1817 kilojoules per mole. The third ionization energy is 2745 kilojoules per mole. And the fourth ionization energy is 11,586 kilojoules per mole. So the large jump in ionization energy that we see is from 3 to 4. And since we have this large jump, when we go from 3 to 4, we can readily remove 3 electrons, but it's very tough to remove the 4th electron. So this means that this particular unknown element has 3 valence electrons. So it's most likely that this particular element is in group 3. And actually, this is the experimental data for aluminum. So using ionization energy, we can kind of look at the trends and remember, when we're analyzing ionization energy, it's the energy to remove one electron from whatever species we're trying to investigate. And we can then use experimental data to try to predict what group a particular element is in the periodic table.